There are other impacts of climate change. If the atmosphere warms, then the ocean warms too. If water warms, it expands, and that leads to sea level rise. Also, if land ice melts, that will lead to sea level rise. And you often see reports in the media about all the land that gets lost due to sea level rise. There's a major mistake in many of these reports, and that is perhaps best illustrated with this picture here. What you're looking at is a picture of a beach, and people enjoying themselves, and there's people sunbathing. And these two here have their heads actually fairly close to the ground, and if the water were to rise by 50 centimeters, which is well within the range of expectations over this century, then they would drown. And this woman here would drown, and he would drown, and so on and so forth. A lot of people would drown because of sea level rise. Now, this is an obviously ridiculous statement. Why is this a ridiculous statement? Well, a projected sea level rise of half a meter, perhaps a meter, takes place over a century. The average time that people spend on the beach is only 2 hours. So these people will be long gone by the time the water has risen. And they have eyes and ears in their head, and when they return to the beach, they actually notice that the water is higher than it used to be, and therefore will sunbathe further inland. Actually, these people will be gone. They will be long dead by the time the water has risen so much, and there's no reason whatsoever to assume that people will insist on sunbathing in the same place as their grandparents did. Now, this is obvious. This analogy is due to Howard Grunsberg, who you see here. This is obvious that sea level rise will not lead to the massive drowning of sunbathers. But the same is true for other aspects, other impacts of sea level rise. We will not let land get lost to the sea. Dike building is a known technique for 5,000 years now. The Sumerians knew how to do it. The ancient Chinese knew how to do it. We haven't lost that technology. We will protect our coasts. And in many places, it's not so much land loss that you need to worry about, but it is the costs of coastal protection that are the main impact. It's the cost of adaptation to sea level rise that is the main impact of climate change rather than the land loss. And that is actually much less harmful than land loss. There is an aspect to this that is often overlooked, and that is wetland loss. If sea level rises, then the natural response of a wetland is that it silts up and you lose land, you lose wetlands at the seaside of it, but the wetland migrates inward, it grows towards the land, and things that used to be dry now become part of the wetland. So the wetland itself is not particularly affected, unless there is nowhere to migrate to. That is, unless the dry coast behind the wetland is protected by seawalls or dikes, then the wetland has no place to migrate to, and it will drown eventually. This is an issue because wetlands are nurseries for young fish, and wetlands are important places for birds and also migratory birds. And they will be in trouble if the wetland shrinks or disappears altogether. Sea level rise is therefore an issue. It's particularly an issue in deltas, low-lying areas, essentially near the coast. It's also an issue in small islands. But again, there the popular perception is often wrong. It is true that low-lying islands, atolls, as you see in the Seychelles, the highest point in the Seychelles is only a meter or so above sea level, but current sea level. So there's well within the range of possibilities that a century from now the Seychelles will have completely disappeared underwater. But there's actually an additional issue there that is much more urgent, and that is saltwater intrusion. Essentially, if you look at groundwater near the coast, and the groundwater is fresh, and then there's all the salty water in the sea, and the two need to be in balance. If the sea level rises, that increases the pressure underground on the groundwater, and what you see is that it adds where the groundwater is moves inland. There's more and more brackish water, more and more salt water intruding into what used to be fresh water, and turns it brackish and therefore unsuitable for drinking, unsuitable for agriculture. Now, that is true along any open coast. It's also true on atoll islands. Often there's a groundwater well under the island. That is fresh water. Sea level rises, then salt water will intrude into that, and that will essentially make the groundwater undrinkable and unsuitable for agriculture. And this is expected to happen within the next few decades. So long before the Seychelles disappear under the sea, they will lose all their fresh groundwater, and that means that these islands will have to be evacuated long before they disappear. And that is actually a much more urgent problem. Not less of a problem, actually more of a problem, because it's so much more urgent. But the key thing here is that there's adaptation. The response to a loss of fresh groundwater is, of course, to desalinate water, which comes at a cost. But adaptation here is key, and that is further illustrated in this picture. What you're looking at is on the horizontal axis scenarios of sea level rise. This will happen somewhere towards the year 2100. On the vertical axis, you're looking in a logarithmic scale the number of people flooded per year, and it includes everybody. So it includes people who get their toes wet, but also people who get their heads wet. So it includes everybody who suffers flooding. And you see three alternative scenarios. Intermediate climate change, a lot of climate change, and not so much climate change. And you also see three different adaptation scenarios. So if we take the solid line, and let's just focus on the red ones, it says that at the moment roughly 50 million people, 60 million people suffer annually from floods, and if sea level continues to rise, then by the end of this century that 50 million people will become 500 million people, and that is quite a dramatic increase. Recall that this is a logarithmic scale. That's why it is much more dramatic than it looks. That is under the assumption that protection levels, or rather coastal protection, stays as it is today. Essentially, the dikes are what they are, and we're not going to change them. That is the solid line that you're looking at here. The dashed line, it's not that the dikes stay the same, but rather that the protection afforded by those dikes stays the same. So if a dike currently protects against a 1 in 100-year flood, sea level rises, then dikes will be raised so as to protect against the future 1 in 100-year flood. And that has an impact, what you can see here. Now the final line here is a different assumption about adaptation, and that is that if you look across the world, then what you see is that richer places and more densely populated places have much better protection against floods than poorer places. If you compare the coastal cities of Nigeria to the coastal cities of the Netherlands, there is a world of difference in how well they are protected. And that is just follows from the demand for safety. If you grow richer, you can better afford to build dikes, and you demand that your government builds those dikes. So if you include that the reason that climate is changing is because people grow richer and use ever more energy and emit ever more CO2, So if you assume that that continues in the future, that is what drives our scenarios of future emissions, then it's logical to also assume, well, people get richer and therefore will demand better protection against these things. If you include that, you end up with this line here. And the key thing here is that, well, the impact of sea level rise is an increase in the order of magnitude of flooding, or number of people flooded rather, but this adaptation is also an order of magnitude. It goes from 500 million to 50 million again. So adaptation is as important a signal as climate change, or in this case sea level rises. And that is an important thing to keep in mind. That is also true if we talk about managed ecosystems. I talked about unmanaged ecosystems before. Managed ecosystems is just farms, essentially. What you're looking at here is the impact of climate change on crops. And it's a complicated graph. There's all sorts of things going on. What we're looking at here is the three main crops that feed us in terms of calorie, the main crops. So that's maize, that's wheat, and that's rice. That's in the temperate zones and in the tropical zones. What you're looking at on the vertical axis is the change in yield, essentially the amount you get off an acre of land. And on the horizontal axis, you're looking at a scenario of climate change, from no climate change to quite severe climate change. So that is what you're looking at. Then the dots are individual studies, and then the lines that are drawn through this are essentially your best fit to those observations. And what you see is maybe what you would expect, that if we look at a cold-loving plant in the tropics, wheat, then you see a quite steep fall in yield, up to 50% or so, for a 5-degree warming. That is quite a dramatic change. Less so in the temperate regions because it's colder still, because it's cold enough still. If you look at maize, which is a heat-loving plant, you see less of a response. If you look at rice, it's another heat-loving plant, you see less of a response. Now, that is the red curves and the red dots. If you instead focus on the blue ones, the difference between the blue and the red is that in the red, farmers keep doing the same thing. So they keep planting the same crop. At the same time, they keep applying the same amount of fertilizer and the same amount of pesticides as they've always done, and they harvest at the same time as they used to do. This is the so-called dumb farmer hypothesis, where essentially the assumption is that farmers stick to the crop calendar of old. They keep doing the same thing that they've always done, that their fathers did and their grandfathers did. People call this the dumb farmer hypothesis. It is really a misnomer, because no farmer is like this. It's really the analyst who is done here to make such assumptions. Because essentially what the farmers are supposed to do is they do the same thing, they see that it fails, and they keep just stubbornly at it, even though their strategy fails year after year after year after year, and their crops keep failing. So in the blue scenario, there is on-farm adaptation. That is, farmers switch, change the time at which they plant, at which they harvest. They may change cultivars and so on and so forth. They actually respond to the circumstances. There's no off-farm adaptation in these scenarios. It's not that cropping patterns change or things like that. If you include this on-farm adaptation, actually what you see is that for wheat, this negative that we had before becomes less negative. The negative that we have here in red becomes a positive. The negative that we have here in rice becomes a positive. And that is because farmers adjust their behavior so as to take advantage of the new opportunities, so as to minimize the bad impacts that can be avoided. And you see that this is basically everywhere in 5 of the 6 graphs. You may have wondered what is going on here. Well, this is a result from the IPCC. And the geniuses that drew this graph forgot to correct for selection. So the secret here is that we're not comparing like with like. There's 120 studies that without adaptation, there's 92 studies with adaptation. If you compare like with like, then actually you see that the blue graph is also above the red graph here. This is just selection bias that for some reason we suppose it. World-leading experts forgot to correct for. So adaptation helps here. There's a final thing I want to say, 2 final things I want to say about this. What you're seeing here is that actually the question whether or not climate is good for agriculture or bad for agriculture depends very much on the kind of crop you're looking at. So rice responds differently to wheat. The different plants, and it also depends very much on where you're looking. You see negative impacts on wheat in the tropics, but positive impacts in the temperate regions. So you can't really answer the question, is climate change good or bad for agriculture, is good or bad for food supply. For that you need to take an additional step, and that is done in this particular graph, where all these impact changes are put, all these yield changes are put into a model of agricultural trade that has an additional effect. One thing is that the impact, the results that I showed here include on-farm adaptation. But if you put it into a trade model, then you also see off-farm adaptation, that in some places crops grow much better than in other places comparatively, and that means that you see a shift in production from one region to the other, and these trade models also allow much more of a shift from one kind of demand to another kind of demand, that you switch perhaps away from a wheat-based diet to perhaps more of a rice-based or a maize-based diet. So those things are sort of adaptations are included in these models as well. The scenarios are the same here on the horizontal axis. We're looking at scenarios of climate change. On the vertical axis, we're looking at the average price of agricultural products across the world. So this is sort of an indicator of what is going on with agriculture around the world as a whole. And these are output prices. Demand is fairly inelastic for food. So negative means an increase in supply, and positive means a decrease in supply. And what you see is that towards the end of the century, all 5 models agree that agricultural production as a whole has fallen, and therefore agricultural prices have gone up. In the shorter term, that is actually, you see a divergence here. You have 2 studies that see bad things happening from the start. You see 2 studies that actually see good things happening initially, that climate change actually stimulates agricultural production and therefore suppresses food prices. The difference between these studies, the blue and the brown, and the green and the purple, is CO2 fertilization. These studies do not have CO2 fertilization, and these studies do have CO2 fertilization. So what is that? Well, plants are carbohydrates. They grow by photosynthesis, that is, they take energy from the sun. Then they take water from the roots, from the soil, and they take CO2 from the air. And then in photosynthesis, they combine the CO2 from the air and the H2O, the water from the ground, into a carbohydrate, CN8, and then they dump the oxygen back into the atmosphere as a waste product, right? Which is good for us. So that is what plants do, but they need CO2 from the air for this. The way plants do this is that they absorb CO2 through their stomata from the air. And one way to picture this is that a stomata is essentially a little mouth that sits on the leaves of a plant that grabs CO2 molecules from the air. Now, if there's more CO2 in the air, that just makes it easier to absorb CO2, and that makes plants grow faster. But there is another more important aspect to this, and that is that these plants need to open their stomata to take the CO2 out. And they are just like little mouths. If you have a cold, and therefore you sleep with your mouth open, you wake up very thirsty because you have been evaporating all that water through your mouth. The same is true for stomata. If they're open, they evaporate water, and that means that plants become thirsty and they need to suck up more water from the soil. So if there's more CO2 in the atmosphere, the stomata don't need to be open that long, and that means that plants become more drought tolerant. And that explains the difference between these scenarios and these scenarios. These ones include CO2 fertilization, which is good for plants, and these ones exclude CO2 fertilization, and therefore you don't see the big positive effect in the beginning for mild climate change.